All right, and welcome to practical geometry analysis of bilateral symmetry and Heatmap. This is an easy-to-follow approach. One of the challenges that researchers do have basically in morphometrics and morphology is in the area of bilateral symmetry or symmetry generally, because it is a technical area, and this course actually unleashed for researchers practical areas of symmetries, or rather bilateral symmetry and the Heatmap in easy way. Bilateral symmetry is a type of symmetry in which the arrangement of the body parts such that a single plane passing through between the upper and lower surfaces and through the longitudinal axis of an organism into right and left mirror images, such as in human we have a bilateral symmetry forming. We have such also in insects and other organism. This particular symmetry also is divided into two. By the way, aside from bilateral symmetry, there are other symmetries that exist, such as rotational symmetry. We have spiral or helical symmetry. We have biradial symmetry. We have translational symmetry, and so many other symmetry. But the common type of symmetry is called bilateral symmetry, mostly in research field, in morphometrics, morphology, and diverse research areas. So we have two types of bilateral symmetry. We have matching symmetry and we have object symmetry. Looking at the A above, it shows a matching symmetry. Look at the A in the image, the wings of the insect. So because the wings are in two sides, in left side, right side, and then you look at the image in the B, object symmetry is the image of a human face, which is divided into two halves, having pair and unpair. So you have two sides of a pair side here, pair side here, and with unpaired in the middle. So this is the concept of symmetry. We are in the matching symmetry. This is when symmetry is studied by matching the pairs, such as the case of fly wings. The structure of interest is present in two separate copies, has mirror images on the left and right side of the both and of the body or the organism. And we can see example of the human hand, left and right hand of human being. For example, this is like the image of the dementia human hand. It's a syndromic image. Okay, so this is left, this is right, and you can see that you can measure the symmetry of this hand using matching symmetry. So because there are two left and right side, the same thing happens like the left and right side of insect wings. You can measure the symmetry, which is called matching symmetry, by the left side and right side. So landmarks will be placed on both of them in the same position homologously. All right. So we have object symmetry as well. In contrast to matching symmetry, the structure is already symmetric because of its internal plane or line of symmetry. The midline in two-dimensional representations, resulting in the left and right halves being mirror images of one another, as in the case of human head I showed just now. And you can also see a sample of the leaf, the pair structure. You can see the leaf is paired now. So you see the on pair side, left and right, all right, and the same thing with human head structure paired. So asymmetry is different from symmetry. It's simply simply the absence or lack of symmetry. All right. Three different forms of asymmetry patterns have historically been identified in nature, depending on the distribution of left-right disparity in a population. Direct symmetry, fluctuating symmetry, and antisymmetry are basically types of asymmetry. But commonly speaking, we have direct symmetry, otherwise known as DA, and fluctuating symmetry, known as FA, that are commonly used to observe hypotheses in research field. All right, so directional symmetry is when a character develops more fully on one side of the plane or planes of asymmetry than on the other side. This is referred to as directional symmetry, or DA, between two morphological structures. But in frontal symmetry, these are the sort of organisms' incapacity to develop along precise determined path. Fluctuating symmetry develops, in that case, unquestionably widespread. FA typically produces equal average development on each side and by normal or normal distribution of the difference between the sides. So we have symmetry. For example, a bilateral symmetry is widespread mostly in animal kingdom. However, most animals can deviate from expected symmetry and manifest some kind of asymmetries. For example, fluctuating symmetry is considered as a tool for evaluating developmental instability in an organism, such as in human, whereas directional asymmetry is inherited and could be used for evaluating evolutionary development in an organism. All right. So we also have a concept of heatmap, all right, in the morphometrics. And this heatmap is something that people find hard sometimes to do. But we have a lot of techniques that is applied to do this in morphometrics, both for matching symmetry and also for any kind of images, rather, that is based on landmarks of the shape. All right. With the heatmap is the formation of TPS, thin plate spline interpolation, based on the landmark data. The intensity of the red hues we are seeing here in this land heatmap plot correspond to the size of local expansions. The blue hues correspond to the local contractions, and the green hues correspond to the roughly invariant regions. So you can see the heatmap of human face, heatmap of human insect here. So this is a sample of what is called heatmap or TPS in morphometrics. If you look at a presentation of result of symmetry or asymmetry, they follow the same pattern. They just depend on what you are hypothesizing. Okay, all of them looks close to this table. If individual is called individual symmetry or individual variation, and we have side. Side means directional asymmetry, which otherwise called a reflection. Otherwise, I call it reflection. And we have individual by size, which is called fluctuating asymmetry, or otherwise called individual by reflection. And we have measurement error. So most time we digitize twice or 3 times in order to find a replicate, in order to have a replicate for measurement error, which is very important in this course. So this is what we will present under this course. When you look at these 2 lines of this red part, they are the most important part of this for presentation of the result. At the same time, we also have the bolding part, which is also the error part in white. This is measurement error, very, very important. So you can see majority of researchers use MS, mean square, to measure the error, while many use SS. Anyone you prefer to use is okay, since you are able to present the analysis appropriately. At the same time, when we're measuring the symmetric significance, we use F and P, all right, to measure. Both F and P are very important in the symmetry or asymmetry presentation of data, or result rather. So you can see here that even in this particular result, 3.78 was given by functional symmetry in F, which is almost 3 times of individual symmetry, individual symmetry in the same F. You can see that, which is significant, which is symmetric. Why the functional symmetry is also 0.03, which is also significant, but D is not. So you can see a lot of things is involved when it comes to delivering results for symmetry and asymmetry. All right. So we will see a lot of practical approach on how to generate the result, both in R and other tools hard programming and other tools that we use in presenting the data or computing rather the data for result for the symmetry and also for our studio. Right, the first thing we need to do is to load our library, Geomorph. If you don't have, you can install. Just type install library package, enter Geomorph, then and you can install. I've already installed, so I don't need to do that again. So just click on run and run the library. So now this our studio, you can use that. You can use RGUI as well. Okay, so then let's bring in our data, our file in now. This particular one, I just copy a few of them just to show example from our dataset. This dataset, just copy a few of them and put in the directory here so that I can show example. Don't want to use all. For example, if I make a mistake now, for example, I want to place my 15 here, this is 13, I want to place my 14 here. I mistakenly placed it here. What do I do? I have to correct it. You click on this guy called edit landmarks. So click here. So you now drag this guy, drag it here. Drag this one. Okay, that is how to correct it. Okay, so this one can happen anytime, so you just know what to do. Then you continue. 16. All right, so this is how to do. So you continue like that, click on next until you finish all the 60 images. So when you finish, you just click on file, save data. So click on this guy, save. All right. So I said that it must go in a proper alignment. All right. Look at this 37 now. So we have this vector 1, vector 2 now. This one. Or Filibu 2, whatever I want to call it. So don't mind the one. This was, you can give any heading here. Don't worry about that. You can give any heading. It can be H1, H2, doesn't matter. So here we have 37. Don't forget, you have here also what 37. So look at it here. 37. You have 1, 6. You have 2, 5. You have 4, 8. You have 20, 22. You have 12, 13. We have 16, 17, we have 19, 21. You can see these are the pair data now. Same thing we have here, all right? So it can come. It doesn't mean that it must be from up to down. Must be sequential like that. You know, it can be from down to up. It doesn't matter. Okay, it can be from middle up down. So just make sure that what you have here is in line with what is here. That's what is important. Okay, so you can change the order here. Okay, the number 9 can go to number 2. But line 2 can go to line 3 can go to line 5. Doesn't matter. Understand? As much as the pair is accurate. What is the pair? All right. So this second data we need now. So let's skip this one. The third file we need is called rep data. Now let's see that from landmark lm equals to let's read our landmark first. Our landmark, let's read land. What's the name of our file again? Face what? Face data. Thank you. All right, face data dot tps. Okay. Then comma space id equals to id. All right. So let's run this line. Or let me just quickly type and run together. GPA equals to GPA equals to GPA. So what do you have? You have LM, comma. I don't want to see the result of printing. Let me just print the result of false. Right. So let me. Let's say GPA. Is that possible? Error. Okay, we have global error, we have asymmetry error, we have symmetry error. So they're not important in analysis unless you just need to want to do with them. So that is what you have for now. All right. So this is how you compute in a Sage very easily. All right. So we are done with what we want to do. We have generated our result here. Okay. So let's go back and see the result what we generated. Go back to our result. Let's see the result. Let's see the result. This result here. Let's click and see from here. Okay. Let's see. All right. So let me position this properly. This is FET, SS, DS, DF, MS. Okay, the same thing we have there. So this one is significant, this one is not. All right, so I'm just trying to arrange properly so that you can view together. All right. All right, so you can see now this is having a P equals to 0 and also this one also 0, but this one is 1, not significant. That's it, NS, not significant, right? So for individual symmetry now, it is symmetric because it is significant, and our F is 4.7, which is very high. Then also sides, which is called a DA, is also significant. The F also 13.6. All right, but the FA is not significant. You can see FA is got 0.7 FA for F, and the value is 1, so not significant. You can see it's showing here not significant. But for look at maneuver, maneuver also corresponds with our result we have here in the Procus ANOVA. Sides here significant 0, sides here is significant also 0. All right, and if by size also here is not significant 0.5, so not significant. So you can see that the significant component and this one are not significant. So you can copy this out how I'm putting your manuscript or your thesis for an analysis, for further analysis or explanation. So this is what you need for now. All right. So we are going to compare this result together with the previous one we did after we have finished. So you see the result. You compare to see what we get and if they are related or if they correlated. All right. So that is that for now. All right. I will see you in the next section as we look at a matching symmetry and the same Sage. Thank you so much for listening. All right. Bye. This is one of the files so I used before. Of a test. All right. Skip. Just skip. You can see it's okay now. All right. So this is how it comes. Okay, you can now where we are going to is parrot, right? Parrot is our major concern here. You can switch between EBS and TPS. All right. So I've explained this before. If you remember, I explained them before. So I'm just trying to explain again. All right. So this is what we have. Okay. Now the way it looks like this because the landmarks, there are not many. All right. So that's why it's forming this format. All right. So this is the PC1 now. This is first principal. This is first configuration. Can call it PC also. They're not principal component actually, but it's the deformation of the configuration. All right. So it is TPS thin split spline. All right. So you can this one is you can go to 2. Let's go to 2. Just click that 2 here. Look at it. How it look like now. Look at it. You can see how it look like. So it's different from the former one. All right. So the data set is the landmark is enough. There are many. All right. So you can now go to Paros now. Look at it now. It's better than the former one. All right. So you can see all the factors coming out. You can analyze it. So look at it where you have more of a blue, more of red, more of. So I explained this the other time. Don't forget. You go and check the previous video where I explain what the color means. Understand? I explained them. Don't forget. So let's go to number 1. This number one, this one, second one, right? Can see how it look like. Third one, okay. So you can export them out by saving them. All right. So you can now analyze them, explain them one after the other. All right. You can check. I will post one of my what do you call it now? One of my journal online. I will post the link here. Maybe just check it. All right, so that you can know what I'm talking about, which already been published in a scientific reports of or nature journal. So it's Q1 paper, so you can check it out. It has this there, but understand you can see this there. It's for Down syndrome. All right, I mean sorry, it's for Angelman syndrome. Yeah, so you can check it out there and understand what I'm talking about. So the other ones here, this one regular grid, you can just put grid behind it, which is very good, okay, very nice. All right, lettered grid. You can see this river, right? Just a vector. All right, so this is how you compute a heatmap using landmark in Morphometrics, and you can see it's very nice. Okay. But let's look at other this. Look at this. How effective this is now. And this look very nice, right? And you can check the parrot of this now. You can see very nice. You can see this. It's very nice. And check number 3. Let's say question 1. Can that look like number 2? Number 3. Of course. Thank you so much. You can watch full video of this course in UDEMY. Thank you so much for joining us. We'll see you later. Thank you.